Today I'm going to talk a little bit about the potential of corals to adapt to climate change. We all accept that climate change is upon us, and organisms are responding in many different ways, and these responses of the organisms are quite profound. So we're seeing effects on physiology, which Ken has just discussed, and earlier this morning Janice Lowe showed us some data showing that the Porites bommies on the Great Barrier Reef are growing much more slowly than they used to. So we're seeing effects on physiology, we're seeing effects on phenology, the timing of reproductive events. The length of the growing season in the Northern Hemisphere is expanding, spring's coming earlier. There are effects on distribution, there are big changes in range size, and this paper by Leslie Hughes was written in 2000, and at this point in time there wasn't much evidence for adaptation. But since this work was published, there has been, and there's a growing field of contemporary ecology, of contemporary evolution. People are realising that some organisms, in some situations, can evolve quite rapidly. So this graph just shows the changes in concentration of carbon dioxide in the atmosphere over the last 650,000 years. So again, it shows that these changes in climate are nothing new, but as people have been pointing out today, we are heading into uncharted territory. So the concentrations in CO2 haven't been this high at any point in this period, and the other difference is that the change is happening very rapidly, and probably more rapidly than it has in the past. Thrown into the mix, of course, is the effect of humans, and so we haven't been that abundant, and our effects on the environment are something quite new. So the other response of organisms, and in particular corals, is that they're bleaching, the frequency and the extent of the mass bleaching events, and it's predicted to get a lot worse. So this is a paper from Simon Donner, published earlier this year. He's predicted that under the business as usual scenario, 80% of the world's reefs are going to experience harmfully frequent events by 2030. But he also went on to make an estimate of how much thermal adaptation would be required to at least slow this event. And so the figure that he came up with was a figure of 1.5 degrees Celsius in thermal adaptation. Now, if corals can adapt that much, it will delay the frequency of these harmful events by about 50 to 80 years. And so the idea is that it'll buy reefs time to allow humans to get their act together and to reduce our emissions. So there's three essential elements if you want to look at the rates of evolution in organisms. There's phenotypic variation in your trait of interest, and that can be environmental, it can be genetic. Only the genetic aspect of that is heritable. Traits vary in their heritability, and also there's the issue of generation times. So organisms with short generation time, like David's gobies, with the generation time of days, can evolve much more rapidly in a given unit of time than can species with the longer generation times like humans. So there's three elements there. Now, one approach for estimating the rates of adaptation, combining all those elements, was presented by Skelly et al. In a paper in Conservation Biology in 2007. And they came up with a formula to estimate the rate of adaptation based on the variation in the trait. So this is the phenotypic standard deviation was the estimate that they suggested we should use, and multiplying that by a per generation evolutionary rate, in other words, the heritability of that trait. And what they did to come up with an estimate was they went to the literature, they did a meta-analysis, they looked at the trait that they chose to look at was what critical thermal maxima, so that's the point at which organisms die, and they came up with a figure of the variation in that trait of 0.62. They also, from the literature, derived an estimate of the evolutionary rate, and this the figure they came up with was, again, 0.25 increase in, they came up with a figure of 0.25 haldane, so that's a quarter of a difference in the trait in one generation. And so the figure that they came up with from these was that organisms, an ideal organism could evolve an increase of 3.2 degrees C in 10 generations. So if you're looking at an organism with a generation time of 5 years, 50 years, they can adapt approximately 3.2 degrees. That's their ideal organism. So what I tried to do was get a feel for the variation in critical thermal maxima in corals. So with some colleagues in Japan, we did essentially a cooking experiment. We looked at two species, Ceratopora hystrix and Parietes cylindrica. We took one nubbin from each of 32 colonies. We placed them in water baths, and every hour we raised the temperature by 1 degree, and we recorded the point at which each one of those nubbins died. So that gives us a mean and a standard deviation around the critical thermal maxima in these two species. And so they're the results. So from this result, you can see that Parietes is tougher than Ceratopora hystrix. We know that from just the ecology that's been done. And it also allows me to calculate a standard deviation. So then what I've done here is plug that into I've used the heritability estimates from the Skelly et al. Paper, and I've multiplied that by the standard deviation in the critical thermal maxima to come up with an evolutionary rate of 0.275 per generation. Now, going back to Simon Donner's work, who suggests that we need this corals need a 1.5 degree change to delay the frequency of damaging events. They need 5.5 generations to evolve that 1.5 degrees centigrade in critical thermal maxima. Ceratopora needs a little bit more time. So now to convert that into a number of degrees per given number of years, I went to the literature and looked for estimates of generation times in corals. Now this is a tricky thing. There's actually only ever been one study that's set out to estimate the generation times in corals. So I put a range here. The minimum is based on the age at first reproduction in those species. In species with a stable age structure, the generation time can approach that of the age at first reproduction. And then the other estimate is one that I got from a paper by Carpenter et al., which is an educated guess based on a lot of people's experience of approximately 10 years for Parietes cylindrica and 5 years for Ceratopora hystrix. So what that gives us is a range in number of years of how long it will take for corals to evolve that 1.5 degrees C change in critical thermal maxima. And so for Parietes cylindrica, we've got a range of 22 to 55, and Ceratopora hystrix, which is a shorter generation time, can evolve more rapidly, approximately 27 to 67. So let's say somewhere between 30 and 50 years for that 1.5 degrees Celsius. Now, I don't want to use this data to claim that corals can adapt, but this is the sort of approach that we need to be putting firmer probabilities on exactly what is going to happen with reefs. And I suppose you could look at it reasonably optimistically if this is in the ballpark, that in 30 years' time, again, it might just give some species enough time to avoid the damage until we can yet reduce emissions and reverse changes in climate.